Hi, today's lesson is about parallel and perpendicular lines, and as you can see from my writing, really this is all common sense today. It just kind of makes sense. What we're looking at here is the solve it, and folks, every section in your book starts with a application problem, and this is the one for section 3-4. Jude and Jasmine, it says, leave school together to walk home. Jasmine cuts down a path from Schoolhouse Road here to get to Oak Street there, and Jude cuts down another path to get from Schoolhouse Road to Court Road, as you can see in the picture. And the question says, what conjecture can you make about Oak Street and Court Road? That's the outsides here. And I would just ask you to look at the angles that are marked congruent here. Right there and right there. Which kind of angles are those? Alternate interior. If those alternate interior angles are congruent, then what we know for sure is that Oak Road and Schoolhouse Road run the same direction. As you look down here where Jude was walking, alternate interior angles here are also congruent, which means that Schoolhouse Road, this one, is parallel to Court Road, this one. And then it's not a far jump to say that if we're parallel here and we're parallel here, then we must be parallel here. So the conjecture that you probably want to say or make is that Oak is parallel to Court, and it's because they're both parallel to the same road, Schoolhouse Road. That's exactly what our theorem 3.8 says. If two lines are parallel to the same line, if two lines are parallel to the same line, then the two lines must be parallel. Again, very straightforward. It seems, I mean, the language seems a little bit weird, but the concept just makes sense. We've got, well, a little proof of that, and you'll notice that I've got some angles that are numbered in this diagram. I'm going to give these lines some names, so I'm going to go with L, M, and N here. And what the theorem says is this: if two lines are parallel to the same line, and that's what our drawing shows, then they are parallel to each other. And in terms of writing the given information, what we have is that L is parallel to M and N is parallel to M. What we want to prove is that that makes L parallel to N in our diagram, N, she says. And I think that we can do that with the corresponding angles that are shown. I think we can show, because of parallel lines and corresponding angles, why this must be true. So let's set that into writing here. L parallel to M, N parallel to M given. Now I'm going to look at the angles that are associated with L and M to start with. Angle 1 is congruent, or must be congruent, to angle 2, because if lines are parallel, corresponding angles are congruent. You'll notice a lot of times I just write the corresponding angles congruent thing. That's not going to be what I want to do here, because eventually I'm going to have to work backwards, so I just want to show it this way first. And that's because L is parallel to M. It's also true that angle 2 must be congruent to angle 3, and that's because if N is parallel to M, its corresponding angles are equal as well. So I'm going to write only the reason one time both of those statements are covered. But if you look at this, folks, this is a perfect transitive property progression of logic. The first thing is equal to the second thing. The second thing is equal to the third thing. So the logical conclusion is that the first thing, angle 1, is congruent to the third thing, angle 3. That's a transitive property. And if that's the case, if you're saying that this angle and this are congruent, well, folks, they're both to the left of a transversal and above their lines. That means that they are corresponding angles which are congruent. And the theorem there says if corresponding angles are congruent, then lines are parallel. So as you think about that, the lines that would have to be parallel based on those corresponding angles are L and N, and that's what we wanted to show. Notice that we used the theorem and its converse. Pretty interesting little proof there. Our application problem for this is a trellis that somebody is building so that vines can grow up on it. And the idea is you want parallel slats that are increase here or rising here, and then they're going to add a series of slats that are on the downhill so that we get that lattice kind of thing. The question says if pieces A, B, and C must be parallel. So that's here, here, and here. If those are going to be parallel, what has to be true of these angles at 1, at 2, and at 3? Well, considering this top line to be a transversal and each of these to be parallel, if that's what we want, then those angles 1, 2, and 3 have to be congruent. They're corresponding angles, and we need them to be equal if we want parallel lines. Okay. Then it says, now we're going to start looking at this piece D. He attaches piece D so that it's perpendicular to A. So let's put a little right angle mark in there. If your answer to part A is true, that is, if these angles are all congruent, is D perpendicular to B and C? And the answer to your question would be yes, because if the corresponding angles are equal here, corresponding angles will also have to be equal on this transversal. So yes, because corresponding angles will all be 90. As we said, today's lesson is really about common sense, and theorems 3.9 and 3.10 involve both parallel and perpendicular lines. They're very similar, they're closely related. They look at the same issue from two different perspectives. You'll notice that we don't have this written in the if-then format, but that's because I just want us to think about what must be true. Suppose that line T is perpendicular to both M and N. So T makes a right angle at M and it makes a right angle at N. What will have to be true about the lines M and N? They have to be parallel. That's the only way that this situation can be true. If this angle is 90 and this angle is 90, then those lines have to be parallel because there's a set of corresponding angles there that are congruent. So the statement of the theorem says if a line is perpendicular to two lines, to each of two lines, then the lines must be parallel. This looks, so here we started with perpendicular and got parallel. Now we're going to start with parallel and get perpendicular. So look at this one. Lines M and N are parallel, so we're starting out with that. Line M is perpendicular to T. What has to be true about N and T? They have to be perpendicular as well, because if these lines are parallel, then that corresponding angle has to be the same as that one. Okay? So if we're going to state this theorem, we're going to say if a line is perpendicular to one of a pair of parallel lines, then it's perpendicular to the other line as well. If it's perpendicular to one of a pair of parallel lines, then it is also perpendicular to the other. That's theorem 310. Both closely related. Again, they look at the same. Look, the pictures look identical. It's just that they're kind of the converse, or they're, yeah, sort of the converse of each other. Let's see how that works out. We've got just a couple of little activities for you to do in your notes today. And the first one involves a proof, proving a relationship between the two lines C and A. It says in this plane, and you have to have that, the term in the plane, because you don't want to think one of these lines might be perpendicular because it's coming straight out from the diagram. No, they all have to lie in the same plane. So it says that C line is perpendicular to B. This line and this one, that's that right angle right there. B is perpendicular to D, so B is also making a right angle there. And one of our theorems just now said, if we're perpendicular, if a line is perpendicular to two lines, then those lines must be parallel. We know that C and D are parallel. Okay? So however C reacts to one line, D will react the same way, and vice versa. They're parallel. The next piece of given information says D is perpendicular to A. That's that right angle right there, D line and A line. But we've just said that however D reacts with a line, C will react the same way because C is parallel. A is perpendicular to one of a pair of parallel lines, so it must be perpendicular to the other. So we're going to use both of the theorems that we got today in this proof. Let's see if we can't get that down in writing. Okay, so we're going to start out with C perpendicular to B and B perpendicular to D. And I am going to use the other piece of given information later in the proof, so I'm going to save that and write it down later. But what we said, if C is perpendicular to B and B is perpendicular to D, C must be parallel to D because B is perpendicular to both of those lines. That was our second theorem. B is perpendicular to both lines, therefore they must be parallel. All right, now we want to add that piece of information that was given, that D is perpendicular to A. Just adding it here because this is where it fits into the logic flow. If these lines are parallel and A is perpendicular to one of them, then it must be perpendicular to the other. So we're going to be able to jump right to this factoid that C is perpendicular to A, and it's because A is perpendicular to one of a pair of parallel lines. Now I know some people would just say, why don't you write the theorem number? That's because I can't remember the theorem numbers. I think that, okay, they were 9 and 10. So this one is theorem 3.9 that we were using. This one is theorem 3.10. I'd rather see the language of it written out anyway, because that really explains to someone, like, I should be able to walk right through this diagram with someone based on my proof and explain to them how I know that C and A would meet at a right angle wherever they meet. I like the language, but the theorem numbers may be helpful a little bit today because this is kind of convoluted reasoning. In this problem it says, could you also say that A is parallel to B? Are you justified in saying that those two lines are parallel? Yeah, in many ways, okay? They're both perpendicular to the same line. Or you could just use the corresponding angles there as well. But this this is today's theorem. So yeah, we could say those are parallel because they're perpendicular, both of them, to line D. So very interesting little lesson today. Pretty much common sense. And I hope that you'll take a look at that. You try as quickly as you can, and then we'll see you in the next class period.